Thank you, Dr. Shuttle. Good evening. First off, we want to thank you all for waiting here patiently. You know, this is a very taxing and demanding day. We want to thank you for waiting patiently for our project. We are the Mengineers, and we're comprised of project manager Michael Kane, technical manager Jimmy White, Danny Ball, and myself, Dev Dasgupta. Our project was T1 measurement optimization and MRI, and was advised by the one and only Dr. Vicky Nakatomidu. Thank you. So tonight, we will go over our vision, despot, our approach, execution, optimization results, a decent video, MRI results, and finally, a summary. So getting into it, the basics. MRI, magnetic resonance imaging. Essentially, a very high-quality imaging modality that shows a great representation of the body, as you can see. And here's an MRI scan of a brain. So what we did was we used a tissue type of MRI, specifically T1. What is T1? T1 is a relaxation time that represents the image, essentially it's the quality of the tissue. So it's used to differentiate between different tissues. And so it's an indicator of various tissues throughout the body. And a good example of T1 in the 3.0 Tesla, which is the magnetic field of an MRI scanner, values for the white matter would be 830 milliseconds, for gray matter, 1300 milliseconds. And for lesions, it would be a range of 2500, 3500 milliseconds. So what does that mean? Essentially, we can figure out what types of tissues are in the body, what types of organs are being scanned with the T1 values. And so T1 is a very difficult value to measure because of the time it takes to measure it. We have a technique which is called despot, which is valuable in the sense that it improves the time and improves the acquisition in order to get a certain T1 values. However, what we want to do is improve the accuracy of T1, essentially improve the range of T1 to include the lesions and whatnot. So with the high accuracy of T1, that leads to improved prognosis and treatment of degenerative diseases down the road. And Danny can further explain despot.
Okay, Despot 1 is a linearization technique for T1 mapping. It provides a very precise T1 contrast. We need this contrast so we can see the difference between the different tissues of the brain. How it works is it measures T1 through a series of SVGR signals with a varied flip angles and a constant repetition time. So here's kind of how SVGR works. The inputs to it are a couple flip angles, you have a TR, and out comes the signal intensity of the SVGR. So if we make this TR constant, we've now made this system linear. So these are the basic equations which it runs off of, and we can see if we plot the signal intensity versus the flip angle, we get a straight line, and if we take the slope of this straight line, we can calculate T1 from that. So it's a measuring technique, despot. So it has limitations. The limitations here are it's only precise up to values of T1 for 2000 milliseconds or less. So to measure precision, we use standard deviation. Standard deviation versus T1 is in this plot here. So right here you can see this is 2000. All the points in blue, the standard deviation is very minimal. Once it gets above 2000, it grows exponentially and the precision is no longer good.
So for us to achieve our goal of extending this range, we need to redesign despot. And we're going to do that by manipulating the flip angles and the repetition time. And to quantify or qualify our optimization, we have three basic parameters: accuracy, precision, and scan time. Scan time we want to keep low because a really long scan time is just pretty much a different scanning technique that will give you great T1 value, but it's a long time to stay in the scan. And we're really going to concentrate on precision because we're measuring an area. So accuracy is almost as important as precision because we need to have a better idea of the range in that area. So we need to run simulations of these scans, and the first thing we need to do is implement Monte Carlo, which is a way of processing lots and lots of data with many random simulations and samplings. And if we run with too low a Monte Carlo, we get bad results. And this is standard deviation versus T1. And if we run with 1,000 that we discovered, then we can represent a decent signal. Now, to get the error and the quantification numbers from this, we calculate a perfect signal, or the SPGR, that comes right from the magnet, and then we add noise with the Monte Carlo 1,000 times, and keeping the SNR at about 50, which is reasonable to expect from an actual scan. And we get the standard deviation by calculating the T1 from this noise and comparing it to the perfect signal in the original.
Thank you, Jimmy. All right, so looking at our three-point design, it involved playing with some very large numbers. We had 3 flip angles, a short repetition time, and a long repetition time to play with. All said, we were looking at about 46 million possible inputs into our system. Now, such a large number obviously begs the question, how do we go about finding the best one? The answer is twofold. MATLAB. And number 2 is implementing what I like to call an information matrix. Now, an information matrix is essentially a model. It's a first-order Taylor expansion approximation that involves a few partial derivatives in the interest of locating the place where signal information is greatest. So this is essentially what the information matrix looks like. The partial derivative should indicate to most people in this room that we're looking for a maximum, particularly where signal information is greatest. So we run our numbers through the information matrix, and this is what comes out. A very nice MATLAB surface plot. What we see here is signal information as a function of our first 2 flip angles. And as we can see here, this is for a set repetition time and a set T1 value. And as we can see here, 3 and 11 were the optimal for this particular run.